This is the third video for the Capacitors and RC Circuits laboratory experiment. Again, I've conducted the experiment for you, and it's basically up to you to provide the analysis for the data that was collected and shared with you. But in this video, for those of you that are unsure about the mathematical modeling step, I'm going to walk through finding one of the two mathematical models. Turns out finding the mathematical model for the charging capacitor is slightly more difficult than finding the mathematical model for the discharging capacitor. So I'm going to go ahead and do the charging capacitor and leave the discharging one for you to work on your own. So here's my graph of charging the charging capacitor. The potential is increasing over time. And so I'm going to go to the Analyze menu and try to figure out which equation is going to best fit that by accessing the curve fit menu. Well, it doesn't seem like proportional would be a good fit, right? A linear equation through that intercept of 0. I could get a slightly better fitting linear equation, but neither of those seem appropriate in this case. And in fact, we discard polynomials for the reason we discard polynomials most of the time, in that if you have a polynomial that's increasing for some time, it's going to then be decreasing later, and that doesn't make physical sense to us. We wouldn't expect, if time went on long enough, for the electric potential to decrease across that capacitor. All right, power series gives you somewhat of a good fit. You can see there the fit's not terrible on that particular model, but not great. And it turns out this experiment is one where you can get a very well-fitting model. Variable power probably gets you, well, it gets worse. Inverse, again, is one that drops off with time, as does inverse squared, etc. But natural exponent, the next one down on our option, actually gives us a really good fit. And in fact, if I hit try fit, you might not have noticed any difference on the screen. That's because the model fits across the data really, really well. The only reason I'm not going to use this one is if I look over here at the coefficients that it tells me, I would really like to make these coefficients have some sort of physical meaning with the system that I was studying. And something negative 2.9, there was nothing that was negative that was measured in our model. And paired with that natural exponent, they put it down a little bit later, is this expression called an inverse exponent. It's the same as the natural exponential function, except it has this 1 minus in here, and that takes care of our negative snafus here. So if I select that instead and say try fit, all my coefficients are nice positive numbers, and that's going to be easier to deal with when we make sense of that model. Also has a really good correlation, 0.999936. I'm going to hit OK, and that adds that equation onto my graph. So that's most of the work, but the format that LoggerPro kicks this out in doesn't tell you if these coefficients have any sort of units. And so there's a little bit of work that we can do to make this model make a little more physical sense. So I'm going to go ahead and put an equation in my Google Doc, except I hit all my menus, which is not brilliant. All right. So I'm going to go ahead and insert an equation here and generate an equation for this expression in a format that we might see in a physics textbook and might be more useful to us. So I'm measuring the potential difference across the capacitor as a function of time. So I'm going to use delta V for my potential difference. And I'm going to put in parentheses T to remind myself that this is a function of time. Let's go ahead and, can we make that larger? Yes, okay. There's the potential difference as a function of time. So that's the potential part of this, equals A. Well, A, LoggerPro kicks out 2.878. I'm going to round because I don't want to write a ton of numbers in here. 2.9, but I got to come back to that 2.9 and see if I think that 2.9 has any units. That's going to hinge largely on what I put here in the parentheses. So again, back to the LoggerPro model, 1 minus, so 1 minus, and then exp is the way the computers write the natural exponential function, but you would see it in a math book as just an e. So I'm going to go ahead and write that as an e and figure out how to raise that to the power of something. All right, so e to the, no, How do I get the power bit here? All right, I haven't used this equation editor a ton. If I actually put in a number, can I raise that up? No. He thinks the equation editor does not like me here. Minus. What if I put in that format to start? The up arrow caret above the 6 worked here. Negative, okay, and then I got C. C is 0.9. Again, I'm going to come back and consider whether that has any units. That's times time. And then we're back down, and we close the parentheses, plus B, and B looks like it's 0.01. All right, now we got to ask ourselves if in this unit anything needs to have, in this model rather, anything needs to have any units to make physical sense. Well, voltage on the left is going to be measured in volts, so every term on the right needs to be measured in volts. And that means 0.1 is going to have units of volts. And ultimately, this expression needs to have units of volts. Well, those units don't come from the thing in parentheses. If you'll recall from your math classes, e to some number is just another number. 1 minus that number, again, just a number, no units. So I need volts on my 2.9 as well. So now I got 2.9 volts times 1 minus e to the negative 0.9 times t plus 0.01 volts. All right, now what about this 0.9? Well, again, e to the some number gives me another number, but I need this number to be unitless. And I'm going to plug a time in here which has units. I measured the time in seconds, and what that ultimately tells me is that the units on the 0.9 have to be inverse seconds, so I'm going to write that as seconds to the -1 power. And it might help if we set that aside in parentheses so that it doesn't get confused with the time in there. And that's it. There is the mathematical model that fits the charging set of data that we collected and has the appropriate units for these constants. How do you actually use this? Well, the easier way is to say, hey, what's the voltage predicted to be across the capacitor at a certain amount of time? So plug in a time here and crank this out, and it tells you what the voltage is predicted to be. Less easy mathematically because it requires some algebra, but just as possible is to say, hey, what time was it when the potential difference of the system was, say, 1 volt exactly? Well, you can plug in 1 volt on the left side of this equation, and you'll have one unknown, namely time t, that you can proceed to solve for. Finding the mathematical model for the discharging capacitor, pretty similar. Again, take a look at those coefficients and make sure that they are positive, that they make some physical sense into what they represent, and you can proceed from there. In this model, what do these constants mean? Well, the 0.9 seconds, inverse seconds rather, relates to how much resistance and capacitance there is in the circuit, and that is addressed in both the lecture and the reading if you've delved into that at all. 2.9 volts. Well, the key to what 2.9 volts is lies in what's in the parentheses here. If I make t 0, e to the 0 power is 1, and I have 1 minus 1, and that whole thing in parentheses is 0, meaning 0 times 2.9 volts is 0, and this tells me at time 0, the voltage of the system should be this intercept term, which in the mathematical model the computer gave us is 0.01 volts. That's pretty close to what we would expect it to be, which is 0 volts. But if you make time really big here, e to the minus really big number is 0, and 1 minus 0 is 1, which means this 2.9 volts is what the potential is predicted to be after a long period of time. And you can look back at your model, and the voltage increased, but then when it got up here to about 2.9 volts, it just stayed at 2.9 volts, which we suspect to be the voltage of the battery, which is what this leading coefficient in the model is representing. All right, that's it. If you have questions on finding the discharging model and you're working with that, feel free to let me know either through email or some other form of communication. I'd be happy to walk you through that process as well.